Welcome to this explainer, where we're going to dive into the ultimate masterclass on chemical bonding. If you've been looking for a complete, highly structured lecture that covers absolutely everything you need to know about this chapter without missing a single bond or crucial concept, well, you are in the exact right place. We're going to transform those complex textbook notes into a clear, structured understanding by looking at the microscopic world as, well, an economy. So let's tackle this central problem right off the bat. Why do atoms bond in the first place? Well, out there on their own, most atoms are incredibly unstable. They've got incomplete outer electron shells, which makes them highly reactive. They're basically on a relentless quest to achieve stability. And in the atomic world, stability means looking exactly like a noble gas. They want to achieve that perfect noble gas configuration, which means either an octet of 8 electrons in the outer shell or a duplet, like helium. Literally, everything we're about to discuss is driven by this one single pursuit of stability. Here's our roadmap for today. We'll start with the quest for stability, move into ionic bonds and trading electrons, look at covalent bonds and mutual sharing, explore coordinate bonds using lone pairs, and finally, compare compound properties. Let's kick things off with Section 1, the quest for stability and chasing those noble gases. Now, technically, a chemical bond is the force of attraction that holds two atoms together. But honestly, I want you to think of it more like an economic transaction. To reach that stable, happy state, atoms have to negotiate with each other. They can lose electrons, gain them, or share them. The type of bond that ends up forming depends entirely on the nature of the specific atoms involved in that negotiation. Moving right along to Section 2, ionic bonds, where atoms are literally trading electrons. An ionic bond, which you might also see called an electrovalent bond, is all about the complete transfer of electrons. In this particular transaction, the metal acts as the seller. It actively wants to give away an electron to become a positively charged ion, or a cation. On the flip side, the nonmetal is the eager buyer. It takes that electron to complete its shell, becoming a negatively charged anion. And because opposite charges attract, a massive electrostatic force locks them right together. Now, here's an absolutely crucial point, especially for exams. For this specific trade to happen, you absolutely need 3 very specific conditions. First, the metal has to have a low ionization potential, meaning it doesn't take much energy to just rip its electron away. Second, the nonmetal needs a high electron affinity, meaning it really wants to accept that electron. And third, you need a large electronegativity difference between the two atoms. Definitely lock these 3 conditions into your memory because they come up all the time. Let's look at this in action. Take sodium, which is a highly reactive metal, and chlorine, a toxic green gas. Sodium is desperate to lose 1 electron. Chlorine is desperate to gain 1. They make the trade, they become oppositely charged ions, and snap. They lock together through electrostatic attraction to become sodium chloride. Yep, that's the perfectly stable, highly essential table salt you sprinkle on your food every single day. Section 3, covalent bonds. So what happens when neither atom wants to give up an electron completely? That brings us to covalent bonding. When you have 2 nonmetals negotiating instead of trading, they form a partnership. They keep their own electrons, but mutually share pairs right in the middle. Because neither atom is quite strong enough to totally rip an electron away from the other, they compromise. And the beauty of this is that the shared electrons count toward the stable octet or duplet of both atoms at the exact same time. Depending on how many electrons the atoms actually need, this partnership can scale up. If they each just need 1, they share 1 pair, which is 2 electrons total, forming a single covalent bond, like in hydrogen gas. If they need 2, they share 2 pairs for a double bond, like in oxygen. And if they're like nitrogen and need 3, they share 3 pairs, creating an incredibly strong triple covalent bond. But here's kind of a fascinating twist. Sharing isn't always fair. If the atoms are identical or have very similar strengths, they share the electrons perfectly equally. We call that a non-polar covalent bond. But in polar compounds like hydrogen chloride, the chlorine is highly electronegative. It's way greedier. It pulls that shared pair of electrons much closer to itself. This unequal sharing creates distinct magnetic poles, a slight fractional negative charge on the chlorine side and a fractional positive charge on the hydrogen side. All right, Section 4, coordinate bonds and lone pairs. So we've covered trading and sharing, but what about the twist in our atomic economy?
What if an atom desperately needs electrons to be stable, but literally has nothing to offer in return? Enter the atomic philanthropists. This is the coordinate bond, also known as a dative bond. In this really unique scenario, one electron-rich atom generously provides the entire shared pair of electrons to an electron-deficient ion. They still share the pair, sure, but the initial contribution is 100% one-sided.
To make this charitable donation work, you need two very specific conditions. First, the donor atom must have a lone pair. That's a pair of valence electrons that are already paired up and not currently busy in any covalent bonds. Second, the acceptor must be severely electron deficient. The classic example here is a hydrogen ion, an H+, which has lost its only electron and is basically just a naked proton. Let's actually watch a coordinate bond form. We start with a perfectly stable water molecule. The oxygen atom is happily bonded, but it has two lone pairs just sitting around. A hydrogen proton, H+, approaches with 0 electrons. The oxygen uses one of its lone pairs to rescue the proton, sharing the electrons to form a brand new bond. Because the proton brought a positive charge along with it, the whole new structure becomes the positively charged hydronium ion, H3O+. You see a very similar thing with ammonia forming the ammonium ion. The nitrogen atom in ammonia has 3 single covalent bonds with hydrogen, but it's got one lone pair left over. It uses that single lone pair to bond with an incoming proton, forming the NH4+ ion. Quick tip for you, when you're drawing this on an exam, the coordinate bond is often shown with a specific arrow pointing directly from the donor atom to the acceptor, rather than just your standard straight line. Now, if you truly want to master this chapter, you absolutely have to understand this exam favorite right here, ammonium chloride. This single compound is amazing because it features all 3 bond types we just talked about. Inside the ammonia part, the nitrogen and hydrogens are held together by mutual sharing. Those are covalent bonds. Then a coordinate bond grabs the extra hydrogen to make the ammonium ion. And finally, that entire positively charged ammonium structure is held to a negatively charged chlorine ion by a massive electrostatic force, an ionic bond. It's literally the ultimate atomic combo. Section 5. Comparing compound properties. Let's zoom out and look at the big picture. How do these microscopic economic decisions actually alter the macroscopic properties of these materials? Well, because ionic compounds are held together by intense electrostatic forces between positive and negative ions, they form really tough, hard crystals. It takes massive amounts of heat energy to break those bonds, giving them extremely high melting and boiling points. Plus, because they're made of charged ions, they conduct electricity beautifully, but only when melted or dissolved in water, so those ions can actually move. On the flip side, covalent compounds exist as separate molecules. The bonds inside the molecule are strong, but the forces between different molecules are super weak. So they're much easier to melt or vaporize, often existing as soft solids, liquids, or gases. And without any free ions jumping around, they just do not conduct electricity. This is exactly why we structured this explainer the way we did. If you look at actual exam worksheets from the source material, they explicitly test your ability to differentiate the exact conditions for ionic bonds, the electronegativity differences, and those electron dot structures we've been covering. Once you understand the why behind this atomic economy, these questions go from confusing to incredibly straightforward. So I want to leave you with this one thought. The next time you sit down for a meal, just take a look at the salts and the water on your table. Think about the massive ongoing negotiation of electrons happening right there in front of you. You now have the complete blueprint to understand exactly how the universe builds itself from the ground up, whether it's through trading, sharing, or donating. Thanks for hanging out with me for this complete masterclass on chemical bonding.